In physics, a conservation law states that a particular measurable property of an isolated physical system does not change as the system evolves over time. Exact conservation laws include conservation of energy, conservation of linear momentum, conservation of angular momentum, and conservation of electric charge. There are also many approximate conservation laws, which apply to such quantities as mass, parity, lepton number, baryon number, strangeness, hypercharge, etc. These quantities are conserved in certain classes of physics processes, but not in all. A local conservation law is usually expressed mathematically as a continuity equation, a partial differential equation which gives a relation between the amount of the quantity and the transport of that quantity. It states that the amount of the conserved quantity at a point or within a volume can only change by the amount of the quantity which flows in or out of the volume. From Noether's theorem, each conservation law is associated with a symmetry in the underlying physics. Conservation laws as fundamental laws of nature. Conservation laws are fundamental to our understanding of the physical world, in that they describe which processes can or cannot occur in nature. For example, the conservation law of energy states that the total quantity of energy in an isolated system does not change, though it may change form. In general, the total quantity of the property governed by that law remains unchanged during physical processes. With respect to classical physics, conservation laws include conservation of energy, mass, linear momentum, angular momentum, and electric charge. With respect to particle physics, particles cannot be created or destroyed except in pairs, where one is ordinary and the other is an antiparticle. With respect to symmetries and invariance principles, three special conservation laws have been described, associated with inversion or reversal of space, time, and charge. Conservation laws are considered to be fundamental laws of nature, with broad application in physics, as well as in other fields such as chemistry, biology, geology, and engineering. Most conservation laws are exact, or absolute, in the sense that they apply to all possible processes. Some conservation laws are partial, in that they hold for some processes but not for others. One particularly important result concerning conservation laws is Noether's theorem, which states that there is a one-to-one correspondence between each one of them and a differentiable symmetry in the system. For example, the conservation of energy follows from the time invariance of physical systems, and the fact that physical systems behave the same regardless of how they are oriented in space gives rise to the conservation of angular momentum. Exact laws. A partial listing of physical conservation equations due to symmetry that are said to be exact laws, or more precisely have never been proven to be violated. Approximate laws. There are also approximate conservation laws. These are approximately true in particular situations, such as low speeds, short time scales, or certain interactions. Conservation of rest mass. Conservation of baryon number. Conservation of lepton number. Conservation of flavor. Conservation of parity. Invariance under charge conjugation. Invariance under time reversal. CP symmetry, the combination of charge and parity conjugation. Differential forms. In continuum mechanics, the most general form of an exact conservation law is given by a continuity equation. For example, conservation of electric charge Q is where is the divergence operator, ρ is the density of Q, J is the flux of Q, and T is time. If we assume that the motion u of the charge is a continuous function of position and time, then in one space-dimension this can be put into the form of a homogeneous first-order quasi-linear hyperbolic equation, where the dependent variable y is called the density of a conserved quantity, and a is called the current Jacobian, and the subscript notation for partial derivatives has been employed. The more general inhomogeneous case is not a conservation equation but the general kind of balance equation describing a dissipative system. The dependent variable y is called the non-conserved quantity, and the inhomogeneous term S is the source, or dissipation. In the one-dimensional space, a conservation equation is a first-order quasi-linear hyperbolic equation that can be put into the advection form, where the dependent variable y is called the density of the conserved quantity equals conserved quantity, and A is called the current coefficient, usually corresponding to the partial derivative in the conserved quantity of a current density of the conserved quantity J. In this case, since the chain rule applies, the conservation equation can be put into the current density form. In a space with more than one dimension, the former definition can be extended to an equation that can be put into the form where the conserved quantity is y, denotes the scalar product, is the Nabla operator, here indicating a gradient, and A is a vector of current coefficients, analogously corresponding to the divergence of a vector C, D, associated to the C, Q, J. This is the case for the continuity equation. Here the conserved quantity is the mass, with density ρ and current density ρu, identical to the momentum density, while u is the flow velocity. In the general case, a conservation equation can be also a system of this kind of equations in the form where y is called the conserved quantity, y is its gradient, 0 is the zero vector, and A is called the Jacobian of the current density. In fact, as in the former scalar case, also in the vector case, A usually corresponding to the Jacobian of a current density matrix J, and the conservation equation can be put into the form. For example, this the case for Euler equations. In the simple incompressible case there, where u is the flow velocity vector, with components in a n-dimensional space u1, u2, S is the specific pressure giving the source term, it can be shown that the conserved quantity and the C, D, matrix for these equations are respectively, where denotes the outer product, integral and weak forms. Conservation equations can be also expressed in integral form. The advantage of the latter is substantially that it requires less smoothness of the solution, which paves the way to weak form, extending the class of admissible solutions to include discontinuous solutions. By integrating in any space-time domain the current density form in 1D space, and by using Green's theorem, the integral form is. In a similar fashion, for the scalar multidimensional space, the integral form is, where the line integration is performed along the boundary of the domain, in an anti-clockwise manner. Moreover, by defining a test function phi continuously differentiable both in time and space with compact support, the weak form can be obtained pivoting on the initial condition. In 1D space it is. Note that in the weak form all the partial derivatives of the density and current density have been passed on to the test function, which with the former hypothesis is sufficiently smooth to admit these derivatives.